Hey students, it's January 14th, and I want to finish up information about how we measure the stars using HR diagram like plots, and how so just some other things. We just need to clean up the topics we have yet to cover. I thought I would actually discuss the astronomy picture of the day today since we haven't done one this week. So I thought that'd be kind of cool. Plus, it's a really awesome one. This is a view from obviously low Earth orbit in the International Space Station. And this star right here on the right across this circular edge, which is known as the limb, you can actually see the upper part of the densest part of our atmosphere actually glowing. But then you can see all these streamers of the aurora sticking up out into this upper region. So the International Space Station actually travels through this part of the aurora. It's in it. And that means that you can get some really awesome pictures, but it also means it's a lot of radiation for astronauts to have to live through or look at and deal with and all that kind of stuff. Anyway, they're Sirius, the brightest star in the northern or southern hemisphere skies for an Earthbound observer. And here's what it looks like from low Earth orbit. As I think they're over Australia, I think it said, if I scroll down here and look. There's a Twitter thread where someone said the aurora was slathering up the sky, which is a very strange phrase. But anyway, would have been a great excuse to hide a dog picture in the links, but they did not. I am at the American Astronomical Society winter meeting 2021, and this guy, Robert Nimiroff, is hosting a talk I'm going to later. So I'll be able to tell you guys a little bit more about what kind of weird stuff they're planning for APOD. All right, so let's finish up the stuff related to the HR diagram. Reminder that the HR diagram does luminosity or absolute magnitude on the y-axis, with the luminosity or absolute magnitude getting brighter as you go up the y-axis, but the temperature scale on the x-axis is backwards. It gets hotter as you go to the left and cooler as you go to the right. And that's because the x-axis is supposed to really be the wavelength, with the shorter wavelength being close to the origin and longer wavelength being farther to the right. Shorter wavelength means bluer, and that means more energy. Bluer photons have more energy. So those stars are hotter. It's again the photosphere of the star is what we're talking about when we're describing a star's quote unquote temperature. It's surface temperature, and there's the anti-jump cannon scale, the Harvard classification scheme. Oh, be fine, gorilla karate me. Okay, just trying to remind you how this stuff goes. This sort of diagonal that runs from the top left to the bottom right, it's sort of wiggly. This is known as the main sequence, and any star on the main sequence is considered a dwarf in terms of size. It's considered main sequence if it's fusing hydrogen into helium as its main energy source in its core. Then there are a couple of other interesting areas. There's this zone over here, which is the red giant kind of cloud. Any star over here is considered a red giant. Any star along this very top edge, whether it's on the main sequence or not, is considered a supergiant. And any star down here in the bottom right, that's the left. Any star down here in the bottom left, that would actually be these. These are considered white dwarf stars. Remember that absolute magnitude requires that we think about all stars as if they're 10 parsecs away. So whenever you're plotting stars on the HR diagram, you can't plot stars at different distances without messing up the relationship. So the assumption for all of these 20,000 stars in this plot is they are more or less the same distance from the observer, or we have accounted for their distance by calculating their absolute magnitude, one of the two things. So we will work next week on some activities where we know stars are all the same distance, but we don't know how distant they are. So that's another thing you can do. You can make an HR diagram like plot if you know the stars are all the same distance away, so that you don't have to worry about that messing up your HR diagram, but you don't necessarily know that distance. That's what I want to talk about today. How do we use the HR diagram and things like it to discuss distance? The typical way to think about this is called spectroscopic parallax. And There's a lot of variability in this in astronomy, but here we are, kind of the Astro 101 level. And besides using parallax, which the Gaia spacecraft is just about to, and I mean literally today, January 14th, they are going to be presenting data on releasing their third data set of distances and colors. Remember, color is temperature. So Gaia is really good at using parallax to measure distance, and that is a great technique. If, however, you can't use parallax because the star is too far away, meaning that its change over a 6-month period in the night sky relative to the distant stars is too small to measure in an angular way, well, then you got to do something else. That's where spectroscopic parallax can help. If you can plot stars that you know are the same distance on the HR diagram, it turns out that we can use that to estimate their actual luminosity and then use 1 over r squared, the inverse square law, to find their distance. There are some things we need to think about, and let's use this one right here. I want to remind you that there are no. I'll come back to the luminosity classes in a minute. We need to think about the fact that some of them are bright because they're absolutely giant and how that messes around with this idea. However, if we can get their apparent magnitude and their spectral class, then we can use the spectral class, the Oh Be a Fine Girl, Kiss Me, or where they are in the scale I'm about to describe to you. Then you can estimate their luminosity, and with their luminosity, which varies as 1 over distance squared, we can estimate their distance. So this is what is known as, so far we've not really discussed this very much because we haven't gotten very far from the solar system. But now that we are finally at distances that can kind of span the entire Milky Way and even nearby galaxies, it's time to discuss the cosmic distance scale or cosmic distance ladder again. Starting from Earth, if an object is fairly close by, including all the way to, say, the distance to Venus, maybe even a little bit further away than that, we can use ground based radar to get a distance. And just like we bounce lasers off the surface of the moon and use the difference in their travel time, kind of a Doppler shift kind of thing to measure distance, that does work. And it's a very accurate way to measure distances. However, most of the objects in our solar system are too far away for radar ranging to work from Earth. So we use parallax and other sorts of similar geometry kind of things to measure things within the solar system. But the parallax distance tool has now been extended because Gaia is so sensitive. It can now extend this stellar parallax rung of the cosmic distance ladder, sorry, y'all, to much larger distances, meaning that the less accurate spectroscopic parallax technique isn't, well, we can now verify it. So you can have Gaia data and you can use the HR diagram, and the two together can give you some sense of whether or not you're right. And if there's a discrepancy between the two, you can investigate why, that sort of thing. I do want you to notice that as we go up the scale, the uncertainty increases. That's the point of this being a cone. It gets less certain as we get farther and farther away. By the way, this about 200 parsecs, this slide is really out of date now. I could definitely make this number farther away than 200 parsecs. I don't know how far it is off the top of my head, but Gaia has taken this little horizontal line and it's moved it up. In fact, I would also say that the cone is more narrow now that the Gaia data has finally been released. But nonetheless, as we use different techniques for measuring distances in the universe, so we started out near the Earth, and then in the solar system, and then nearby the sun, and now we're talking about distances in the Milky Way. Now we're talking about between here and Andromeda and other close by galaxies. And once we get out of the local group of galaxies, we're going to need another rung on this spectroscopic parallax uh, ladder, I guess we'll call it. So this will come up again, but spectroscopic parallax is where you use the HR diagram to estimate the luminosity. And once you have the luminosity, you can use 1 over r squared, not to get the size of the star, but to get the distance. Remember, luminosity varies as 1 over r squared. Okay, so there are some caveats to this. We've got a problem based on these things called the luminosity classes. And it's kind of hard to see here, but that says 1A and 1B, Roman numeral 1A, 1B, then 2, then 3, then 4. And anything on the main sequence is considered a luminosity class 5. So the sun, which is a G type on the anti-Cannon scale, it's a G2. In fact, remember, G0 would be brightest in that scale, G9 is dimmest. So G2, and then a 5 or a V. It's sometimes called a G2V, even though the V stands for 5. But people say it as V anyway. So the thing is, if a star is on the main sequence, then the HR diagram is going to be perfect. But if it falls into one of these luminosity classes, so these are giants, these are giants, these are supergiants, the size of the star can actually mess around with that calculation. So it can be a little bit misleading to try and find the luminosity. So we often will take a spectrum of the star, and then you can use the width of the features, these absorption features right here. You can see this guy's wider than that one. So this is a K2, a K1b, this is a K5. The wider it is, there are a lot of caveats to what I'm about to say, but in general, if it's wider like this, then you can assume it's probably closer to the main sequence. As a matter of fact, this one is a main sequence star. If it's narrow like this, which actually means it's going further down, which means it's brighter, which means that this line up here, which is how bright the star is, it's kind of like having a shadow. So this has a really kind of dark shadow. This one has less dark shadow. That's another way to think about these. And that's really a metaphor. So it's not perfect, but that's what I mean by the spectroscopy being used to find which of these classes it's in. And by the way, spectroscopic in this context is really referring to the color, but you can also take the spectrum of the star. So be careful about, even though the distance scale works with the HR diagram, we do have to do a secondary kind of investigation. Is it one of these luminosity classes, or is it just 5 and you're fine? So what about masses of stars? Well, if you can see them, like in the case of this pair of stars, Kruger 60, we can literally watch one star orbit the other in the case of a binary system, or if there are more stars like the Alpha Centauri system, I think it's 3 stars. If you can literally see the stars visually, that's what's known as a visual binary, and you can use Kepler's law to figure out how long it takes this star to go around that star. And we actually did a lab where we found the mass of a central star by measuring the orbital parameters of the planets. It's the same exact thing. The little star's motion can tell us about the big star's mass. So that's great, but that's not very common. It's not common to be able to visually see the 2 stars separated. So what do? This is where we have to take the spectrum of a star. Take the light from the star, send it through a spectroscope or a spectrograph, split it into its constituent colors, look for absorption features in the atmosphere of the star, and once we are locked on to features that we know represent, say, hydrogen, which is what these lines would be, what we can do is see how far they've been shifted to the left or to the right. So this top row shows in a lab, somebody took some gas, heated it up, and then you can see these absorption features. So this is what you would expect to see if you're discussing the absorption of hydrogen in an atmosphere of a star, if it's not moving relative to you. But if it is moving relative to you, here you can see red shifted light. It's off to the redder side, the left. Here you can see blue shifted light. It's off to the left, sorry, the right or the bluer side. And then back down again, you can see the lab reference. And so you can see that it's literally been shifted a little bit to the left or a little bit to the right, either red shifted or blue shifted. So you can actually measure, say, the rotation of a pair of stars. And by the way, we can even do this for a single star. We mentioned for the sun has Dopplergrams taken of it every day. So you can even do this for an individual object. But in the case of binaries, if we can't see them individually, you can still detect that the bigger star is being sort of tugged on gravitationally by the little star by watching their pair of spectra zip back and forth. It'll seem to shift left, then shift right. And that's over the course of days, months, weeks, or even years, depending on how close together the two stars are to one another. You may have to take multiple spectra over the scale of years to see the wobble back and forth. By the way, this same exact technique can be used to find planets. This is not the only way, but a common way to detect the motion of a planet around a star, because the planet also pulls on the star gravitationally and makes the star wobble, the starlight shift red and blue like this. It's the same exact technique. So this is one way to find spectroscopic binaries. And then once we do that, we can again estimate the mass of the two stars using pretty straightforward physics. So here's another way for binary stars to give you the mass of a system. This is the most common way, by the way, to find planets, what I'm showing you here. And this is supposed to represent a film strip. You can see a series of images here. So there's the small red binary companion going in front of its yellow other star, other companion. And the here on this far left frame, we should have this much light, some of it red, some of it yellow. In this second frame, a little tiny bit of the yellow has been blocked as the red star goes in front of it. So, and remember, luminosity varies as t to the fourth. So the red one is a little bit cooler. It's kind of like a sunspot. You should notice that the overall yellow has now dipped down in terms of brightness because some of it's blocked by the red star. And then here it's back to both of them shining at us. Now look at number 4. This is an interesting sort of feature in the video. We've got both of them, just the yellow with red blocking it, both of them. Now the red is actually gone. So this would be the light from just the yellow star. So the difference between them is the red plus the yellow. And we can use the fact that there's a big dip, little dip, big dip, little dip. This is known as periodicity. You can actually look for this weird periodicity and you can find planets or binary stars. And then we can use the same Kepler's law stuff that we can use in these other circumstances to measure the mass of the bigger star. So if that sort of technique won't work, if you can't figure out whether or not it's a binary star and get really good information about it, then you're stuck estimating. And this is known as the mass luminosity relation. There is a strong correlation between the luminosity of a star, we're not talking about binaries necessarily now, but a single star, and its mass. And it turns out to be proportional to, which is like this little sideways 8 or an infinity with the far right side lopped off. L, luminosity, is proportional to mass to the 3.5 power. So 7/2, 7 halves power. That weird relationship, and the physics is not all that hard to figure out. We could definitely work through with some logarithms how we would get there, but that's not such an important task for us to do. The reason this is important, as long as a star can be reasonably expected to be on the main sequence, then this relationship will hold. If the star is not on the main sequence, it's probably not going to work. If it's one of these big boys, then the mass luminosity relationship is something else completely. Okay? So what we're really saying, let me get back, as long as I know that the star, I gather data and I plot it, I get a spectrum, I'm like, this is a main sequence star. Then whatever the luminosity is I can actually solve this relationship, and the equation's a bit longer, but nonetheless, I can solve this relationship for the mass instead of the luminosity. So I can take the 2/7 root of luminosity, and that'll be proportional to the mass. So that's another way to estimate the mass of stars. And since stars are so, whenever we've got a whole bunch of stars and we plot them on the main sequence, that means the luminosity turns out to be directly proportional to the mass in a way that we can figure out. Okay? So some math can be applied. If stars are too small, by the way, then they would never get to the point where fusion would be stable. They would get ripped apart. So notice down here on the far bottom, these little tiny red stars are what are known as brown dwarfs. They have a little bit of hydrogen fusion happening in their cores, but not enough to make it stable. So once a star is fusing hydrogen into helium in a stable way, it'll actually end up on the main sequence. That's actually our next chapter. And then you'll notice this is 2/10 the mass of the sun, 1 times the mass of the sun, 5 times the mass of the sun, and 15, and they're all main sequence stars. So, if you have these different pieces of information and you know that they're main sequence stars, you can plot them on this sort of chart and figure it out. So I wanted to show you that the distribution of stars is really mostly small little guys. That 28% are dwarf stars, 41% are red dwarf stars, meaning they are less than a quarter the mass of the sun. So these are really small. These are 28% that are about a quarter to half the mass of the sun. Look how much this of the pie these two segments take up. And then if you add in the 19% of the half to one, this is the vast majority of stars in the Milky Way. So when we're looking at stars throughout the galaxy, most stars are the sun size or smaller. Only a little tiny segment are the really big ones, blue giants, yellow giants, the super giants. That's a really small segment of stars. So when we look up in the night sky and see the big bright stars that are bright because they're giants, that's actually not the most common thing. Most of them are small and red. In fact, the small ones and are far enough away in a lot of cases that we can't see them with our naked eye. We'll need a telescope like, say, WISE or the eventual James Webb telescope, which hopefully will be launched in 2022. We'll see. So here's an actual plot of a correlation. I'll remind you that just because a data set is correlated between X and Y doesn't mean that it's guaranteed to be true. So you need to have a secondary claim. You really need to be able to back up your correlation with some kind of reasoning, because correlation does not imply causation, right? You just having the correlation is not enough. You better have another thing underlying your plot. And in this case, we've got a physics equation that backs up what we would expect. So notice that this is the radius in terms of mass, and there's a pretty strong correlation between radius and mass, but it's sort of fuzzy. Now, they're definitely, from a educational research standpoint, this is a really strong correlation. Whenever you're plotting data from like students' tests, this will be a really tight correlation. It's just that the radius versus mass is not quite as strong a correlation or tightly correlated as luminosity and mass. And the reason is the radius of the star can be affected by a bunch of different kinds of chemistry things that are not in the equations that we've talked about. Now, astronomers do know what this is, but it is more complicated, and it's almost like a case by case kind of basis. Trying to correlate radius with mass. But luminosity versus mass is tightly correlated, especially on the main sequence. And even for stars not on the main sequence, there's still tight correlation between, say, all supergiants and mass, and all red giants and mass, and all white dwarfs and mass. So the different correlations could be done, but it is a fairly tight correlation between the actual luminosity of a star and the mass of that star. Okay? And then finally, what does that mean for how long a star stays on the main sequence, which is what we're going to call the lifetime of a star. So the sun is going to have a total of 10 billion years on the main sequence. And how did we figure that out? It's because the lifetime, which is how long a star fuses hydrogen into helium, this thing down here, is proportional to 1 over the cube of the mass. Let me say that again. The most important factor for how long a star stays on the main sequence is the mass of the cloud that formed it and becomes that star. So if you are looking for a way to predict how long a star fuses hydrogen into helium and therefore glows on the main sequence, its mass is the most important thing. You can, however, relate the mass and luminosity. We could take the different relationships we've seen and figure out the time. But the tightest correlation, or the most useful piece of information, is how massive is the star. Other factors are really just so you can figure out the mass of the star. So that's actually the only reason we talked about it. Okay. So little tiny red stars are going to burn for more than 1 trillion years. That's a ridiculous amount of time. Remember, the universe at this point is 14 billion years old-ish. So the sun is it's been fusing for hydrogen into helium for 4.5 billion years. It's going to keep doing that for another 5.5 billion years. So stars like the sun, about a 10 billion year period. But the little ones, they go for much, much longer. So what does that mean for the big ones that are like supergiant stars. Those stars are going to live the shortest lives, and they actually have the most impressive end to their life because they often explode in a supernova explosion. So think about it this way: the more mass a star has, the faster it will burn through it. The burn rate of hydrogen into helium is the highest when the mass is high and the lowest when the mass is low. Okay, I think that's enough to go through all of the UT homework questions for the week. At least I hope so. And I hope you enjoyed seeing APOD today because I know I've been missing telling you all about it. So next week's going to be a normal week. I'll see you then. Good luck with your HR diagram coding lab. Have a good day.